Hi, this is another aircraft instrument. This is a fuel flow indicator from United Instruments. So as you can see, there is an analog display and also a digital one. So on the front there is this switch, off and MEM. And here there is a small push button. So the indication is in gallon per hour. So this is the hidden plate of this instrument. It is difficult to read. As you can see that the input is 78,000 pulses per gallon. So the input is the frequency signal. So there is a date here, 84. The serial number is 353 here. And on the rear of this instrument there is a typical connector. So let's open this thing in order to see what is inside and if we can do something with this. So one screw is secured here. Okay, so we can see we have 3 PCBs here, and we can see that we have standard parts like these 5% resistors and these capacitors, etc. So these are standard consumer products. So these parts are not avionic qualified or something like that. We have a plastic dip, standard tantalum capacitors, standard resistors. We have some transistors also, so these capacitors seems also very standard. And we have Japanese transistors, 2SC 982 here. Okay, so maybe we try to remove this screw here. You can see that the gears are very thin. Actually, this seems to be a galvanometer. Okay, so we have 2 galvanometers actually, one for each needle. So let's disassemble this thing to see the boards. Okay, so we have 2 LM2907. That code 8344. It is very easy to remove the spacer. Okay, so here we have some CMOS logic, 1TC4020. That is the purpose of this one. So this is a 4093, 4068, I don't know, a 4013, so this is a dual D flip-flop, another 4020, and the 4069 X inverters. Okay, so on the other board there are also some logic ICs. So this is 4511, so this is a BCD to 7 segment driver, classic one. TC 4010, I don't know, and TC 5051. And here it is written DAN 403. So the power supply of this thing is 28 volts, I think. Yes, okay, I didn't see. It is effectively 28 volts DC. It is written here. So there is maybe a voltage regulator or something on this board, I'm not sure. Yes, okay, I didn't see. So there are 2 regulators here, one 7812 and one adjustable, classic LM317. So we can try to supply this thing. So So the input voltage is probably this wire here in red. So it goes to one terminal of this connector and also on the input of the 7812, and it goes also to this diode here with the filtering capacitor. So we can try to supply 28 volts across this capacitor. Okay, so I have 20 volts here. Okay, so let's see what's happened. We have nothing. Maybe we need a higher voltage. I can try to activate the switch. Nothing. The other one. Nothing too. Okay, I'm going to test the supply voltage of these ICs. Okay, so we have 12 volts here. There is a switch here. And when the switch is pressed, there is a counting. It is maybe used for test purposes. I have connected the decad box to the ground. For the moment there is a 1 kilo ohm resistor in order to protect this thing if there is an overcurrent. And we can see that if I connect this terminal here to the ground, there is some kind of movement of the right needle, and here the left needle. So this is maybe the two inputs. So I will connect this terminal to a function generator and we will see what happens. So I have applied one input to a function generator and we can see that effectively this thing works. This thing responds to the input frequency. So the maximum scale is achieved for an input frequency of 1 kHz approximately. 1.05 exactly. So this is the fuel flow actually. And normally the fuel used should be displayed on the digital display here. So we can see on this switch here that we have a square wave at this line here. So this is a self-test. So I guess that this line, this yellow wire here, is a counting input of the fuel used here. So I guess that this blue line should have some pulses when the input is activated. But as we can see, we have nothing here. So the power supply is turned off now. And we can see that this blue line is connected to these X inverters here. So we'll need to follow this wire and see if there is a signal to activate this input here. And this line goes to this AND gate here. So this is the 4068. I don't know this part. So the 4068 is a 8 input NAND or AND gate. So I think I will have to do a small reverse engineering of this board. It is not complicated because there are several gates and it can be difficult. So this is an output of this gate effectively. And we have several inputs. It seems there are some configurations here. So this is maybe a counter, and the AND gate probably provides the prescaler value. So effectively the CD4020 is a counter. So this is this one here. And this jumpers permits to set the counter setting, so a prescaler value. Some outputs are connected to the AND gate, and the AND gate probably provides a reset of this counter. Okay, so I will do a small schematic of this board directly. So I have printed the first page of all the datasheets. So there is this counter, this one. There is a quad trigger NAND gates 1493. So this is the AND and NAND gates with 8 inputs and the classic flip-flop here. So the input actually is a switch, is a selector. So there is a test function here. So this is the normal mode and this is the test function. So the test function, there is a square signal here. Okay, so I will draw this thing on the right because this is the output actually. So this goes to the front board. So here there is a square signal. So I don't remember. Okay, so this is the blue. Okay, so the blue wire is connected. Okay, it's connected to an inverter, the output of an inverter. Number 10. And number 11 goes to the second via here, and this goes to the output of the counter here, number 13. Not the counter, but the AND gate, sorry. And the number 13 is the inverted output here. Okay, and this one goes also to this AND gate here. Okay, and pin number 11 should go to the reset of the counter. Okay, there is a resistor here. There is a counter here. And this goes to the reset line of the counter, number 11. And there is a resistor also. Probably in order to realize a small delay. This resistor is this one here, 51 kilo ohm. Okay, and the input of this NAND gate here corresponds to some configurations, to some data. So this is the different. Okay, so the middle position is the input of the NAND gate here, and it is connected either to the output of the counter, otherwise it is connected to the power supply. What is interesting to know is this line and the clock input. So number 13 of this NAND gate here, and number 13 is connected to a wire here which goes to the front board here. Okay, so number 13 of this line is connected to this orange wire. Okay, so we can check the input of this counter. So the input is pin number 1, pin number 10 for the 4020 here. So this is this one. Okay, so number 10 is an output also. This is complicated. So number 9 is also an output of another NAND gate. 1 and 2 are connected together. I'm tired, it was correct. Okay, so pin 8 is connected to an output also. They are connected together. Okay, and we have some RC network at the input in order to generate small pulses. Okay, so we have a resistor connected to ground here and a capacitor which connected to the output of this flip-flop here. So we have 51 kilo ohm here. So 1 is number 13 of the flip-flop. So this is effectively an output. And the second one is obviously connected to the second output, which is pin 1. So pin number 6 is connected to ground here. So we can check the clock input. So the clock is number 3 and number 11. So pin number 3 is an output of the 4069, and there is a feedback resistor. So pin number 5 of this D flip-flop goes to an output, which is number 6, and number 5 goes to a wire, yellow, goes to the second board. So what is interesting is this signal here. So this goes to another resistor of 100 ohms. And the capacitor, this goes to an output also. This is number 2. Okay, so this is so let's see the second flip-flop here. Pin number 9. Pin number 9 is connected to pin number 8 of another inverter. And pin number 9 is connected to brown wire here, which is connected to this board. So the LM2907 are actually frequency to voltage converter. So these two parts are used to display the fuel flow. So the output of these parts drive directly probably the galvanometer. So we can see that this brown wire is connected here. It's connected to pin 1. So this is the input. So this is the input frequency, and the second one, the yellow, is connected to the second one. So at the output of this NAND gate, we have the pulse, which correspond to the left and the right channels, and we have a counting of both pulses actually. But this is strange, so maybe there is something wrong here, because normally you should expect something symmetrical here, but it is not the case. Actually, I made a mistake. Effectively, 9 is the data and 11 the clock. Okay, so we can see that it is not the same edge between the two flip-flops. We can see that we have a sampling of the input data at different time. So this avoids the missing of one pulse. So normally this should work. If it works in test mode, there is no reason that this thing doesn't work with the normal input. So we can check with the oscilloscope what is wrong with this thing. So I'm going to turn on the power supply and we will make some measurement on this thing. Okay, so I will apply a frequency of 1 kHz or something like that. So we can check, for example, this input signal at this point. So this is number 5. So we have nothing here. Maybe the other one. Okay. So we have something at this point here. So let's see number 13. Okay. So this is number 13. You can check pin number 3. Okay, so we have some pulses here. And number 10. Okay. So there is something wrong when I measure with the oscilloscope the signal at this terminal here. We have a negative pulse, a very short pulse, but there is nothing at this terminal here at the output of this inverter. So this is the signal at the input of the inverter gate. The output, terminal 10, you have nothing. The oscilloscope is on the normal mode. Okay, so there is no trigger. So there is probably a problem with this gate inverter. So I will try to find the one in my stock. I don't know if I have this part. So the output of this inverter actually is connected to a counter which is on this board here. So this is a TC5051. This is a counter with a BCD output. This one. So this gate is connected to the input here, pin 10. So actually what I will do is that I will cut the output of this gate and connect the input of the counter to the input of this gate. It will be the same. Okay, so I will cut pin 10. And I will connect pin 10 here. I have cut to the input here. Okay, it is soldered. So let's see if it is better now. I am going to turn on the power supply. Okay, we have 0. So actually it works now, but the counting is very slow because at the maximum fuel flow there is 50 gallons per hour. So this corresponds approximately to 1 gallon per minute. So we should have an increase here every minute, and it is the case actually. So the problem was a faulty 4069. So we can test the functions also of this push button and this switch here. We start with this one here. Okay, so I will press the push button here. Okay, so this is maybe a display test. It is written CK. And the other one, I don't know. It is not obvious. There is a position off and a position mem. So there is no effect. So I don't know the purpose of this switch. This was the teardown, repair and test of this fuel flow and fuel use indicator. The quality of the construction and the parts used are not the best I have seen. Thank you for watching and see you next time for another video. Bye.